Hi, I'm Sala, and in this video we are going to define what a force ellipsoid of a robotic manipulator is and plot such an ellipsoid with a MATLAB example in a redundant robotic manipulator, planar and without gravity for simplicity. In previous videos, if R was defined to be the position of the end-effector, this here, then its speed was the robot Jacobian times the angular speeds of joints 1, 2, and 3, and if we were not interested in the orientation of the end-effector, then the Jacobian was 2 times 3, and we spoke about the so-called manipulability ellipsoid, which was the set of feasible end-effector speeds when the joint speeds were in the unit sphere. Maybe with some scaling you normalized, so this will be scale Jacobian and the normalized angular speeds in the unit sphere. We also saw that if somebody exerted some force at the end-effector and we wished to counteract it, this will be my end-effector, without robot movement, then the torques at each of the joints, torque 1, torque 2, torque 3, to counteract this force which has two components, x, y, well, the needed torque has this expression. So indeed the Jacobian transposed is 3 times 2. So our goal now is to define an ellipsoid associated to this equation I just encircled in yellow, which will be named the force ellipsoid. And it will be defined as the locus of the feasible forces with joint torques less than 1. Maybe with some scaling we'll discuss in a minute. The basic idea is that if the joint torque is somehow limited, then if this force is too big, my joint motors will not have the capability of counteracting it. So which is the largest force I can counteract according to this formula is what motivates the definition of this force ellipsoid. Of course, a torque in the unit sphere means that tau transposed tau must be less than 1, so the equation of this unscaled force ellipsoid is straightforward from this one. Indeed, tau transposed tau is equal to, well, tau is J transposed F, and tau transpose is F transposed times the Jacobian. So this is the quadratic inequality that the force vector must fulfill in order for it to be cancelled with a torque within our limits. And of course, this quadratic inequality defines an ellipsoid like this, being M Jacobian times Jacobian transposed, a 2 times 2 size square matrix. So this is the force ellipsoid. However, maybe we need to incorporate scalings if the peak torque of each of the joint drives can take a maximum value different from one joint to another. So if we define our scaling as tau in physical units equal to some scaling matrix diagonal E tau times a normalized tau, so this normalized tau is the one that must be in the unit sphere, so this scaling will contain in the diagonal elements the maximum joint torque of each of the joints. So when this tau is 1, then it will multiply by its maximum value in physical units to give the maximum tau. So once I have this scaling, if I replace here this E tau normalized, then I can write that tau normalized is equal to the inverse scaling times the Jacobian transpose times F. So subsequently, the transposed that appears here at the left will be E tau minus 1, because I am assuming this scaling is just diagonal, J F transposed. So this thing lower or equal than 1 is what will define the so-called force ellipsoid with scaling, and this is it. Theory is no more. The ellipsoid defined by this quadratic inequality will be the locus in the end-effector force plane, describing the feasible forces in which the scaled normalized torque has norm less than 1. So let us see how to do this in MATLAB, but it just is easy. We'll name this matrix as M and we'll draw the ellipsoid. That's it. So we'll have a manipulator with these equations being x3, y3, the end-effector position R. We'll study some poses. For instance, the first one will be this one. The Jacobian will be a horrible matrix full of sinus and cosinus, whatever, but when replacing the angles by the pose we are studying, I get this numerical Jacobian. This is the inequality we just justified in our theoretical discussion. And if the torque scaling is, let's say, 4, 3, 2, meaning that each of the 3 joint torques has 4, 3, and 2 maximum torque respectively, then if I call this the scale Jacobian, and M is the scale Jacobian times its transpose, I am just coding this in MATLAB in this line, and the ellipsoid F transposed MF less than 1 that I discussed in the theoretical development, well, in here, just for cosmetic issues, I will draw that ellipsoid centered in the end-effector position that I called ROP. In this code, you can download it and inspect it. But as I said, the ellipsoid has force units, the end-effector position has position units, so I cannot actually carry out this difference, and I am carrying it out just for cosmetic reasons to draw the force ellipse with the center at the end-effector. The thing is that, well, with this 4, 3, and 2 maximum torque at each of these joints, then this red ellipse is the force ellipsoid we were discussing. This is it. So it seems that forces in this direction are the easiest ones to compensate, and forces in this direction are the most difficult to compensate, because we saturate our joint torques sooner. Of course, this will be related to the eigenvalues and singular values of Jacobians and M's and whatever, but we'll defer that discussion for the next video for brevity here. In here, let us just consider another couple of poses to grasp the idea on this as follows. I'll consider now this pose. then my Jacobian will take a different numerical value, and this will be the force ellipsoid. It's somehow more rounded, it seems. And if I now test this pose, which is close to a singularity, I get a different Jacobian, and here I have the force ellipsoid. Let me change the axis. Here we have it. So in this case, I am close to the singularity, so this ellipse is ill-conditioned, and then I have a low force in this direction, but I am able to counteract a large force in the perpendicular direction, in the blue arrow, because yes, it seems that such a force is almost aligned with the robot, so the torque required to counteract it is much lower than in the difficult maneuver in which the force is sort of perpendicular to the joints, so it exerts a larger torque. So in this case, this force ellipsoid is ill-conditioned, and I can counteract very large forces in one direction, but small forces in another ones. Of course, the actual magnitudes depend on scaling, the pose, etc. And as I said, they are related to eigenvalues, eigenvectors, and singular value stuff. But for the moment being, we'll end the video here, leaving that detailed discussion for the next video. So this is it. Thanks for watching.